Hello, thank you for joining us today for our webinar entitled The Platform Behind Accelerating Life-Changing Diagnosis. I'm Brett Hannigan. I'm the Director of Scientific Partnership here at DNA Nexus. I'm excited to introduce two of my colleagues I've been working with closely. First, Aaron Friedman from Amazon Web Services, who will talk about some of the recent changes or recent additions they've made to the AWS platform in their pursuit of working strongly with the genomics community. Then also my colleague Gavin Stone, the Vice President of Marketing from Edico Genome, who will talk a little bit about the Dragon software they put in place that allows for the rapid identification of new variants in genomic information. Before we get started, I want to give you a little bit of what you can expect. We would welcome any questions that you may have during the webinar. We'll hold all questions till the end, but please feel free to input your questions during the webinar, and we will answer them at the completion. Also, we will be recording this webinar and sending out a link so that you can replay it at a later time after the meeting concludes. Again, thank you very much for joining us, and I'll now turn it over to my colleague, Aaron.
Yeah, hi, everyone. It's a real pleasure to be here today, and I'm thrilled to be joined with two of really AWS's premier partners in the genomic space, DNA Nexus and Edico. They're doing some really transformative work, and I'm really excited to be part of this webinar today. So I want to start off at a high level and really describe, why we're seeing, companies across whatever industry really gravitating towards AWS. And when we think about this, at a high level, we see, several themes emerge. The first is by not having to worry about provisioning their own data centers, customers, have the ability to really be more agile, innovate faster. And you can think of, genomics, for example, as a classic representation of this, where if you're trying out different genomics algorithms, you have the ability on AWS to quickly go from a, compute standard sort of CPU-based architectures to GPUs to FPGAs with a matter of clicks, rather than having to go through and really provision new infrastructure, pay all this CapEx up front, which leads into a lot of the cost savings. As with cloud service provider like AWS, you only pay for what you use. You don't have any additional hardware that you're paying for sitting around unused. So the capacity that you provision is the capacity you use, nothing more, nothing less. And we do this by giving you really elastic ways to spin up and spin down your compute and other AWS services. And really this leads back into sort of the utility model, for usage. And when we look beyond, the sort of traditional services of, compute and storage, really what we find is customers, as they, grow on AWS, becoming more and more mature. And the last thing really is, as they grow, they have the ability to go global in a matter of minutes. And on the next slide, really this is to show the breadth of the AWS platform. We're not going to go into any of these specifically, but as I mentioned, before, really, we offer a set of AWS services that are tailored to any part of your workload. So whether it's traditional services or workloads that involve storage or compute, or perhaps big data analytics or data warehousing with Amazon EMR or Amazon Redshift or Athena, you really have the ability to spin up and use services as you need them. We offer, container-based services, batch processing services as well. So really you have the ability to use whatever type of tool that you need, and our goal is to provide that to you to make you successful. And one of the ones you'll hear a lot about today is Amazon Elastic Compute Cloud, or EC2, which is really one of our foundational services. And you can think of Amazon EC2 as virtual servers that are hosted in the AWS cloud that you can quickly scale up or down as you need to. And because you have this elastic model of provisioning, you only pay for what you use, and you have the ability to use whatever operating system you're familiar with, whether it's Windows workloads or your favorite Linux flavor, CentOS, Red Hat, SUSE, our own Amazon Linux. You have the ability to use whatever you are familiar with going in. And when we think about what instance types and what we try to provide customers, we recognize that many workloads are unique. If you think about genomics, for example, there are different, depending on a step in your pipeline, whether it's alignment or variant calling or annotation or some of the downstream analysis, you may have different compute, storage, and memory requirements. And as a result, we offer a very wide variety so that you can pick what you need when you need it. So these are things like general purpose compute, compute optimized for some of the HPC style workloads. We have, GPU-based instances as well, or high memory instances should we need it. But one of the things that, we've noticed customers asking for in the last couple of years is hardware acceleration. And when you think about, massively parallel processes such as alignment and variant calling and problems that are now becoming pretty well defined, accelerating those problems on hardware makes a lot of sense. So at AWS reInvent last winter, at the end of November, early December, we launched our F1 instance family, which are Xilinx FPGA devices that are housed on EC2 instances. And currently, we give you the option either to use an F1 2 extra large, which contains one FPGA, or a much larger EC2 instance, which is the F1 16X large, which contains 8 different FPGAs. And one of the things, going back to this concept of going global, again, we recognize that customers are processing genomes across the globe. When you think about, for example, some of the population genomics initiatives that are happening, in Asia, in Europe, in the US, and elsewhere, really, we try to provide a global presence. And we do this over 16 AWS regions, and those regions are contained of multiple availability zones, which you can think of as one or more data centers in a geologically distinct region from one another to protect against things like, natural disasters, et cetera. But, as we onboard new services, new instances to different AWS regions, customers have the ability to immediately adopt them without having to go buy a data center or rent space in a data center, provision, do all of those things. So they're able to quickly spin up. And you can think about, the F1 instance family really is been emblematic of this. We launched this in general availability earlier this year, several months ago, in our US East region in Virginia. And we quickly expanded that to US West and Oregon, as well as to our Dublin region in Ireland. And you can imagine that we are, very rapidly going to be expanding out to other AWS regions. And our goal, again, is to do this so that you're successful. And, when we start to think about genomics on AWS, there are customers and AWS partners from every industry doing genomics, whether it's large pharma or large startups like Human Longevity, or public sector customers like the NIH or the Precision FDA or the American Heart Association. Customers from any walk of life really are doing genomics on AWS and doing so in a big way. And I think when we get back to that elasticity conversation, it really makes sense, right? Because genomics at its core is bursty compute. You have a genome that comes in, you need to do processing, you need to scale down. If you're running, say, on large sequencers, you often are producing, obviously multiple genomes worth of data at the same time when a sequencing run ends. You need to spin up the infrastructure and spin it back down rather than have to provision for peak. And on this slide is a sampling of customers and partners that are on AWS, but I'm really pleased to be here today with Edico Genome and DNA Nexus, who are doing just some excellent work on top of us. And I'd like to hand it off to Brett again to tell you a little bit more about what DNA Nexus is doing.
Thank you, Aaron. Yes, so as Aaron gave a great introduction to the benefits of using a cloud environment for doing genomic analysis. And what I'd like to do now is tell you a little bit about our platform, the DNA Nexus platform, and how we try to make doing genomic analysis in the cloud very easy for our customers to perform. So a quick background on DNA Nexus. DNA Nexus, we're a cloud platform that sits on top of cloud providers like Amazon Web Services. And we built on top of that an API server that makes it very easy for you to communicate, organize your data, set up collaborations, and run analyses in a batch type fashion. That platform that we've built has a very strong security and compliance layer to make sure that the data that our customers put in place can be provided in a HIPAA and CAP/CLIA compliant manner, or make sure that the data, the IP that they're generating is always safe and secure. We're also developing an ecosystem for our customers so that they can make use of best practices tools, such as the Edico tools we'll talk about shortly, and really allow for them to do the data analysis that will provide the data insights that will drive genomic data science forward. So this diagram is a quick cartoon diagram showing what the DNA Nexus platform looks like. On the top, you'll see an icon showing the storage and the EC2 instances that AWS provides to us and that we can provide to our customers. In the center is our API layer, which allows our customers to organize, manage that data, set up these collaborations. And there are multiple ways that our customers can interact with that API. So we have a web UI that's very friendly and allows customers to see a view of their data and organize it and set up collaborations very easily. But what we find a lot of times is the heavy bioinformatics users like to script their analysis, like to set up automatic runs to be launched. They can do that through command line interface tools that we provided, or even language bindings through Python and JavaScript and that sort of thing. We're currently in use in a lot of different environments. So we have a large vertical in pharma and biotech. Companies like Regeneron, Johnson & Johnson, Novartis. We also are working closely with a lot of government projects. So we've worked closely with the Precision FDA initiative that Aaron alluded to earlier, for instance. Also, large consortia like the ENCODE project makes use of our platform. Then also clinical and healthcare companies like Natera, who are doing prenatal testing so that they can check on the development of the fetus as it's developing, are all doing their work on top of DNA Nexus. And this slide sort of shows you the type of collaboration and relationships that we're able to build up on top of the platform. What you see here is each one of those nodes is a different project on top of the DNA Nexus platform. And each of the edges is that project being shared with some other group. So what you can see is that you have some groups, like the Natera group over here in the bottom left-hand corner, which are pretty self-contained. They have many projects that are being created to do their data analysis, but most of those projects are kept within the Natera community. We have other groups like this University of Washington group in the upper left-hand corner, which is part of a consortia like CHARGE. They create a project and they may share that project with other groups, like a group over in Regeneron or a group over in Baylor. And you sort of are building out this network. That's kind of what one of the roles that we see DNA Nexus is providing the ability to create these networks of interactions so that collaborators can bring their data, put it into a central location, and then multiple people can bring their own data analysis tools and act on that data in a central place. So what does that look like when working on the DNA Nexus platform? So what you see here is a screenshot of our web UI client in a given project. So this project, you can see it looks for all intents and purposes like a Mac Finder window or Windows File Explorer. We have folders on the left-hand side. We have files on the right-hand side. We can do things like rename the files, drag and drop. Essentially, it looks like the world's biggest hard drive. You can have as little as a few megabytes in a project, but I've had projects where I've had over 40 terabytes in that project. It expands and contracts as needed, just as Aaron was referring to previously. That elasticity is really important for genomics analysis. But also equally important is the ability to set up collaborations, share that data with other users. I make that really easy. By clicking on that the green button in the upper right-hand corner, share, you can easily share that data with other users, and you're able to specify what permissions they have to that data. You can say they only have the ability to view that data, to upload data into your project, but maybe they're also able to run analysis inside of your project. Or maybe you want to be more restrictive and prohibit them from copying the data into their own project or even downloading that data. You are granted the ability to specify what level of permissions you want that user to have. And in addition to sharing projects with individual users, you can also set up shares with groups of users through constructs that we call organizations or orgs. So you can imagine if you're working inside of a pharmaceutical company, maybe you're part of the oncology group. So rather than add each individual member of your group to a given project, you could just share it with oncology. And then everybody who's a member of that group would automatically be able to interact with your data. Also, one of the key aspects of genomic data is that many of the countries around the world are deciding that the patient data for their citizens is so special that they need to restrict where that data resides. They want to make sure that the data is protected and it is protected by the force of law from the country where they live. So AWS has made available many different regions across the globe. Inside of DNAnexus platform, you also have the ability to create new projects and specify the region that data should reside in, but still have a single pane of glass view into those projects. So in this snapshot, you can see that I have 3 separate projects. Each one of those resides in a separate region. That's shown over here on the right-hand side by this region field. The first project is in the Germany region. Second project is in the China region. And the third project is all in the US region. All of these are in the AWS platform, but each one of those is a separate region. So a user now who is using China patient data could create a China project and upload the patient data into that China project. All that data would always reside inside of China, but they could share that project with users outside of China, and they would be able to bring their own data analysis, perform that data analysis on EC2 instances inside of China, and still abide by the locality restrictions imposed by the Chinese government. The platform is meant to be very, very flexible. So at DNAnexus, majority of our work comes from people making use of Illumina data. They're going to be uploading data, perhaps streaming it straight from their Illumina sequencers straight into the platform. But we also have a number of customers that bring in a large set of other data types. So maybe they use PacBio data, maybe they use Bionana data, maybe they use Kinnex data or other data sets. We even have some customers who bring in computational chemistry workflows that they want to do computational molecular dynamics modeling, that sort of thing. The platform is meant to be eminently flexible and allow you to bring whatever data type you want to analyze, bring it to the platform, and then run it with the tools that are applicable to that data type. We try to make it very easy for you to bring whatever tool set you want to use to do your analysis inside of the platform. We do that through the use of what we call DNAnexus apps. On the left-hand side, you see sort of a description of what an app contains. An app is described by an app contract that's describes what the inputs and the outputs of this particular app are. A short little script that could be written in Python or Bash that says, take these inputs, run this command line to produce these outputs. And then some set of binaries or other containers that actually has the code that's necessary to run that app. We make use of common open source tools like Common Workflow Language or the workflow description language WDL, so that users can bring their pipelines that they develop from those workflow languages to bear on the Data Nexus platform. You can also bring your own Docker containers to the platform and use those as a means to carry your underlying binaries to perform your data analysis. But some of the most interesting work for me has been our collaboration recently with Edico Genomes to bring their Dragon pipelines to the Data Nexus platform. So as Aaron mentioned previously, Edico has leveraged the AWS F1 instances that have the FPGA cards in there to create incredibly rapid variant calling pipelines so that they can go from FASTQ all the way to VCF at an incredible speed. So on our platform today, users have the ability to run 3 different Dragon pipelines. A pipeline that takes it from FASTQ all the way to VCF. This can do a 30x whole genome in about an hour and a half. If they already have their samples mapped to a reference genome, they can start at a BAM file and take the BAM file all the way to VCF. Or if they only want to map the files, they can take the FASTQ file to BAM. So this is sort of what is available on the Data Nexus platform. Users can take their existing Illumina instruments, for example, and then have the data uploaded to the Data Nexus platform. They could upload that manually, or they could have it set up so that the data is streamed from the sequencer automatically to the Data Nexus platform. Once the data is in place, the raw data from the Illumina sequencer would need to go through a BCL to FASTQ transition. And once the FASTQ is in order, those can be processed through the Dragon pipeline through VCF. That VCF then could be added to additional tools on our platform. So it could be annotated through tools like ANNOVAR or SNPF, SNPSIF. It could even be exported to other tools that would do further annotation or tertiary analysis. It could even be generated external reports that could then be passed back to the end user. Today, if a user wants to use the Dragon FASTQ to VCF pipeline, this is what that would look like through our web UI. On the left-hand side, it shows what inputs are required. Obviously, you need FASTQ files for your input, and then a reference genome. And then by clicking go, the F1 instance would automatically be provisioned. The FASTQ files would be placed on the F1 instance, and the Dragon pipeline would go, and at the end, a VCF and BAM file would be generated as output. In about an hour and a half if it is a, say, 30x whole genome sample, or for an exome sample, that can be done in as quickly as half an hour or so. So yeah, this is lightning fast. A typical industry best practices pipeline of BWA plus JDK might take 15.5 hours using a 35x whole genome sample. But as I've mentioned, Dragon makes that incredibly fast, only about an hour and a half for that same sample. And the great thing is you're not giving up any sort of quality when you go for this incredible speed. See here, we took an example of a genome in a bottle data set. Genome in a bottle is a consortia that is run by the National Institute of Standards and Technology, or NIST, to show what the precision and sensitivity of different variant calling pipelines is. You see here, you get almost as good, if not better, results from the Dragon pipeline as you would get from a standard JDK best practices pipeline. The final benefit is that you've got great cost for this. Currently, we have trial pricing in place that allows you to do up to about a 45-fold coverage whole genome sample at only $20 per sample. If you're only working with smaller samples of exome, that's only $5 a sample. So I want to conclude with a final example showing why this rapid speed really can make a very big difference, especially in clinical care. So both Edico and DNA Nexus are partnering with Rady Children's Hospital for diagnosing newborns who have some supposed genomic disorder that is diagnosed very early on. So there was a case recently described by Rady Children's Hospital where there's a young child who was born, and not shortly after birth, they started developing tremors and convulsions, and they didn't know exactly why. They suspected an underlying genomic cause. So they ordered sequencing, but they also started treating that patient very early on. They have their own sequencers in-house. They're able to take that sample, run the sequencing, and then get the data back incredibly rapidly, run that through a Dragon pipeline, and get the sequence, do analysis and interpretation on that, the variants that were called on that whole genome sample, and they're able to do a diagnosis in as little as 2 days. In under 2 days, they went from child being born, taking a sample, getting it all the way to called variants and an interpreted result that they then chose to switch from the current treatment to a different drug. And that caused the child to, the tremors and the convulsions to be reduced. And ultimately will impact the child's care going forward. That gives you an example of a clinical case where this time to, the incredible speed that Dragon is able to offer really makes a big difference to the underlying care. So with that, I want to hand it back over to my colleague Gavin, who will tell you a little bit more about the specifics of the Dragon pipeline.
Thank you very much, Brett. And yeah, I'm very excited to have Dragon now available on the DNA Nexus platform and have all the fantastic technology that we've developed here accessible by all the users just with a couple of clicks of a mouse. So, okay, here we go. So I want to just start out and kind of put big data into perspective and specifically big genomic data. And this is really a run-up as to why using FPGAs makes such a massive difference, specifically in genomics, but it's also applicable to many other areas. And the first step in kind of grasping this concept is really understanding how big is big data. And kind of an easy way for me to understand that is to make an analogy of, if you take 1 byte of data being equivalent to a grain of rice, and then you start scaling upon that. So when you get up to a megabyte, you've got several bags of rice. You start getting up to a terabyte, you're already filling a couple of container ships of rice. Petabytes, you're already starting to blanket Manhattan. Exabytes, you take out the entire US West Coast. And then when you get up to a zettabyte, you basically fill the entire Pacific Ocean with rice. And a zettabyte is kind of important because if you look at the projections for how much genomic data is going to be produced by 2025, genomics is going to be producing about a zettabyte of data. The data being generated by all these other big data producers really gets dwarfed by genomic data in this time frame. So whether it's social media or online videos or space data, all of that is going to be eclipsed by what we're producing here in the genomics industry. And that really produces a pretty significant challenge because we're currently or have been reliant on CPUs, central processing units, to analyze this data. And the reliance there is that these CPUs are going to get faster and cheaper and be able to analyze more and more data every 2 years. And this 2-year mark is kind of what's known as Moore's Law. It was coined by Gordon Moore, one of the founders of Intel, where if you look back over the past 4 decades or so, these CPUs have been doubling in processing power every 2 years. And you can argue whether that's coming to an end or not, but we won't get into that discussion, and we can just assume that it's going to double every 2 years indefinitely. The problem there is that genomic data is doubling pretty much every 7 months. So it becomes very difficult to solve a big data problem that is growing at a rate faster than your solution is growing. So you really need some kind of alternative technology to address your big data challenges. And for us, our big data challenge is obviously genomics, but this holds true for any kind of big data. So what has really become a technology that's been moved to the forefront over the last couple of years is something called FPGAs. It stands for Field Programmable Gate Array. And essentially what it is, it's a processor, I guess kind of similar to a CPU, except that it's more like a blank canvas, and that you can design any kind of circuits that you want and put it into this FPGA. And it's fully reconfigurable, so you can design any number of sets of circuits and replace the circuits an infinite number of times inside this FPGA. And it really takes a matter of 2-3 seconds to do that. So the fundamental difference really between an FPGA and a CPU is that a CPU, if you want to execute an algorithm or implement an algorithm, you code that algorithm in software. And then when you're performing that algorithmic function, you execute all these many lines of code that transform your inputs into your output. And that takes a non-instantaneous amount of time. When you're implementing that same algorithm in an FPGA, you're doing it very differently. You're not executing lines of code. You're actually taking that algorithm and you're developing a logic circuit to perform that algorithmic function. And the difference there is if you put your inputs into this logic circuit, you essentially get your output at the speed of electricity or pretty much the speed of light. So it's ultimately efficient. And then what you can do beyond that is take that circuit and you can replicate it many thousands of times. So unlike a CPU where maybe you've got a 12-core CPU and you can do 12 things at the same time, execute 12 of these instruction sets at the same time, on a FPGA, you can take that highly efficient logic circuit and you just replicate it many thousands of times. So not only do you get this efficiency, but you get this massive parallelism that is just completely unachievable through any other means, other than implementing what is known as an ASIC. And those are pretty much like the chips that you find on your cell phone, where you've implemented logic circuits, but you implement them in such a way that they're no longer reconfigurable. Makes them cheaper and smaller and lower power, but you lose all that flexibility. So the FPGAs maintain that flexibility and have all the other benefits. And since we're not trying to operate them in a battery-powered device, we don't need them lower power. And the cost now has become significantly low enough that they've pretty much gone mainstream. And if you look at what Aaron was saying earlier, and how AWS have implemented these at scale, this is something that was, completely unthinkable a few years ago, and now everybody on the planet has got access to an FPGA within a couple of minutes at a very low cost. And we take full advantage of that. So because what we've developed is reconfigurable, we're able to take the entire suite of Dragon applications and make them available through AWS and as applications on the DNA Nexus platform. And what that has enabled us to do is provide all of these pretty unique value propositions that Dragon has to anybody that is able to access the DNA Nexus platform that's powered by AWS. So the one thing that Dragon is very well known for is its speed. It's blazingly fast. Brett was saying 90 minutes for a whole genome at 30x coverage. And yeah, that's available today. We'll continue to make that faster through optimizing and making kind of the overhead surrounding the actual analysis quicker. So streaming data out of S3 storage rather than copying it. And that's also the 90 minutes is on a 2x large F1 instance. We're working hard to bring support for the 16x large instance, which is significantly more powerful and will reduce that time down to minutes rather than taking over an hour. And really, as Aaron was saying, the power of AWS is that it's very flexible and very scalable. So you can burst when you need it. You can scale out incredibly quickly. And we showed that, we demonstrated that last week, where we scaled out 1,000 F1 instances. We ran 1,000 genomes at the same time, and we set a Guinness World Record for that. And as you saw earlier, it's very inexpensive to run a whole human genome or an exome. There's currently this special offer pricing that we got running, where it's only $20 to run a whole genome, $5 an exome. And to top it all off, Dragon is one of the most accurate suite of algorithms out there. And this is validated by the latest Precision FDA challenge, where Dragon performed across the board better than any other of the other entrants that were in there. Specifically on indels, we had a very strong performance. So at the moment, you've got our germline application that's available on DNA Nexus. Brett showed you a few different variants of that, where you can run the whole pipeline from FASTQ to BCF, or just mapping and aligning, or just variant calling. We're busy working very hard to, over the coming weeks, make the next set of applications available. And those include our somatic pipeline, our RNA pipeline, and our germline V2 pipeline, which is the pipeline that we used in that Precision FDA challenge. It's got all of our advanced error detection algorithms that produced that incredibly high accuracy. So the accuracy numbers that Brett was showing you earlier, that's for the V1 germline pipeline. We encourage you to take a look at the V2 pipeline that performed so well on the Precision FDA challenge. So in addition to these pipelines, we also got another application that we're working hard to make available, and that's our BCL conversion. So going from BCL to FASTQ very, very rapidly, supports all of the different Illumina instruments, including their new NovaSeq instruments. And then beyond that, we've got a significant number of additional algorithms that we have on our Dragon platform that we're working hard with Brett and his team to turn into DNA Nexus apps as well. So Brett showed you kind of what was involved in creating an app a little bit earlier. And yeah, so we're taking our pipelines and turning them to apps. So over the coming months, we will be releasing many more of the Dragon pipelines on the DNA Nexus platform. So we've spoken a little bit about it. At the moment, as far as pricing goes, Dragon's only available to run on the 2x large instances, but stay tuned. We'll be making it available on the 16x large instances in the near future. Pricing at the moment, like I said, $20 for a genome, $5 or $6 for an exome, and that's valid through the end of this month. So definitely encourage you to go and test it out this week. And from next month, it goes up to regular pricing of $32 for a genome and $9 for an exome. And I just want to end off with really driving home the fact that even though Dragon is really well known for its speed, that it's not simply the speed that sells. And we highlighted earlier why speed is really important in kind of the children's hospital scenarios. But for that speed to be meaningful, you really have to have a solution that's incredibly accurate as well. And that's what Dragon is. We have all these customers around the world in the biggest sequencing centers, children's hospitals, government institutions. And really what drove their decision to start using Dragon has been the ability to not only analyze things quickly, but to analyze them incredibly accurately. So it's really a testament to the team that we have here at Edico, the amount of effort that everybody puts in to make sure that these are undoubtedly the best performing algorithms in the world, not just from a speed perspective, but from an accuracy perspective and just from an ease of use perspective, so that secondary analysis becomes a solved problem. You don't have to worry about tinkering around under the hood. It now becomes an app and a workflow that is much bigger than secondary analysis. So on the DNA Nexus platform, you simply just go and drag a Dragon app into your overall workflow, and you can then go and focus on much more interesting things than going and reinventing the wheel over and over again when you want to perform secondary analysis. Choose a solution that's fast, that's very low cost, and is highly accurate. And I'm sure you guys have got much better things to do with your time than just going and reinventing the wheel over and over again. So thank you. I'm going to hand it over back to you, Brett, and we can finish things off.
All right. Thank you, Gavin, and thank you, Aaron, and thank you all for joining us again. Again, if y'all have questions, please feel free to put those into the question form below. I see that we have a number of questions already, so I'll go ahead and read those off and we can answer those. So the first question was asking whether the figures that we provided for the genome in a bottle data set, whether that was for SNPs plus indels or what the accuracy metrics were calculated based on. So yes, those were the specificity and sensitivity metrics for SNPs and indels combined. Somewhere I also have the results split out by SNPs and by indels separately. So if you're interested in that, please feel free to follow up with me and I can provide those to you. But it was a similar story that the results for Edico's Dragon was as good, if not better, than the GAK best practices for SNPs and for indels. The metrics I gave were for the combined. There's an additional question about for the $5 for an exome, whether it was bundling multiple samples per instance. And in fact, right now, no, that's not what we're doing. We're a $5 per single sample of exome. So it goes in, spins up, processes the exome, and then delivers the results. So if you had multiple, you would launch multiple jobs. There could be efficiencies gained by batching exomes. And so if you have a large number of exomes that you want to analyze, again, please feel free to ping us and we can talk about how we might be able to do that. Okay, let's see. There was a question on how many instances were needed to achieve the 1.6 hours runtime on 35-fold whole genome sample. That's a single F1 2x large instance, so one instance. On the 16x large, that would actually be even faster. And so as Gavin mentioned, we're in the process of trying to put that in place on the larger instance as well. There was a question about pricing, about introductory pricing. So yes, the $20 for genome and $5 for exome, that's introductory, good through the end of the month. After that, the pricing will be $32 for the genome and $9 for the exome. And I think there was a question about databases for Oracle and SQL on AWS. So I'm going to let Aaron take that one. Aaron, do you want to answer that question?
Yeah, sure. So, first thing, but before I talk really briefly about our sort of managed database services, you can run any database on Amazon EC2. You can imagine that as your own virtual infrastructure. So we have, customers running MongoDB, or if they're running, Hadoop MapReduce, which obviously isn't a traditional database, but it has a lot of similarities. We have a bunch of customers running Cloudera, Hortonworks, et cetera. As far as our managed database offerings go, so from traditional relational databases, we offer managed database services that cover pretty much the whole gambit of most of those. And those are managed databases. You don't have to worry about provisioning, et cetera. You just say, I need this size database and go. And we offer that for Oracle, SQL Server, Postgres, MySQL, MariaDB. We also offer our own sort of optimized flavors of the open source tools or open source databases in the form of Amazon Aurora, which can give customers, up to 5x performance improvements, similar types of cost reductions there as well. Beyond that, we have a managed NoSQL database in Amazon DynamoDB, which is a massively parallel key value store. And then beyond that, we also offer data warehousing with Amazon Redshift. So if you need to scale to, say, petabytes of data to store in a data warehouse in a columnar format, Amazon Redshift is a great choice. One of the other, two things, just as a related note, that I've seen a lot of customers use recently that is applicable to genomics is with Amazon EMR, which is sort of our managed Hadoop framework, also contains, the ability to use Spark or any type of distributed tool, as well as Amazon Athena, which is managed Presto. So you could literally store your data. You have a Hive, catalog that you connect to, and then you can actually query the data as it sits on Amazon S3, and it's quite fast. That I think covers most of it, and then of course we have a lot of partner solutions in the space as well, if you're interested.
Okay, thank you. So a couple of additional questions. Let's see. There's one question about being able to process larger samples. So currently, I said we're limited to around 45-fold coverage or 90 gigabytes in total file size. And yes, that is something we're working on, and we should have out, I'd say, in the next couple of weeks. We're just finalizing what pricing would look like on that. There's a follow-up question to that question about processing price and time increase with the depth of the sample. So the processing time will increase with increased sample depths, but the cost will be bucketed. So right now, basically the way that the apps work on our DNAxis platform is that we look at what the file sizes are as a proxy for coverage depth. So if it's less than 20 gigabytes in total file size, then we charge the exome rate. If it's between 20 gigabytes and 90 gigabytes in size, we charge the genome rate. And that is a flat fee per run for anything within that range of file sizes. And we anticipate doing something similar for something on the order of 90 gigabytes to 200 gigabytes. Right now, we're doing it based upon file size, gigabytes. We actually will transition over to a estimate on the actual coverage depth that we will get from sniffing the FASTQ file and the BAM file as input. But that's what that looks like today. Okay, let's see. Are there any other questions? There was a question about other organisms. So human is what we're talking about here, but what about for mouse? So yeah, the pipelines should be very flexible. On the DNAxis platform, we've made reference genomes for mouse, for human, and a couple of other organisms that are slipping my mind right now. But if you have any other organism, it's very easy. There's actually an app on the platform to take a reference FASTA and can generate basically an index file for the Edico tool to use. Then you can provide that as input and sequence. The underlying cost, again, right now we're just doing based upon what the file size is. So it'll look at how big those files, input files are, and charge based on that. Okay. So there's a follow-up question about relating to mouse and human mixed. So yeah, I'm not familiar exactly how that type of analysis typically is done, but whatever you do in a typical variant calling pipeline should be able to be done through the Dragon pipelines as well. Basically, you provide the past user's input, you need a reference genome. And you can create that reference genome through the use of tools. Gavin, do you want to elaborate on that?
Yeah, so we've already got customers that are doing that specifically with the mouse and human genome mixed. So happy to share more information on that. We'll get the person who asked the question details and respond with a lot more information. But essentially, we've got customers running almost every species that's out there. Anything that has a reference, we can run it all the way up to wheat genomes that are massive and down to bacteria. And it really doesn't matter as long as there's a reference for it, we can do it.
Okay, I think there's another question that just came in, Gavin, that you might be able to help with. They asked what the quality of the result is if you use lower depth of coverage on like 10x or 5x worth of coverage.
It would be a drop-off.
Yeah, I mean, there's obviously going to be a drop-off. We've got some advanced algorithms that they're on that list there that are coming in the future that will be able to provide the same level of accuracy and performance with lower coverage, but you're obviously going to get a decrease in performance with accuracy and with coverage depth. We have customers that do very low coverage for specific applications, so we can handle like 0.2x coverage, but it's for a different application than doing variant calling.
Okay, thank you. So I see an additional question from someone asking about data ownership on the data going through the Edico pipeline. So inside of DNA Nexus, when the data is on our platform, we don't share that with anybody. In fact, we can't ourselves see it unless you give us explicit permission to the data. And so when you run the Edico pipeline on our platform, we process the data. We don't see it. We don't send that data outside of our platform. So there shouldn't be any concern about that data being shared with third parties. Okay, any other questions? Okay, I think that answers all of the existing questions. And with that, I'll once again thank our speakers, Aaron and Gavin. I really appreciate you joining me here today to talk about the really exciting work that Amazon has done and Edico has made available for the genomics community. I know our customers are very, very excited to try it out, and we've had a number of customers that have run dozens and hundreds of samples already. And again, I thank you, all of you, for joining us today. If you have additional questions, please feel free to contact us. You see the contact links here on the platform or on the screen. Happy to follow up with you on any additional questions. And again, we will send out links later to this recorded session so that you can rewatch or send to your friends and colleagues. Thank you again, and we will talk to you later. Goodbye.